What is this?
Ladies and gentlemen, welcome to the lesson for today. Soon, we shall be taken on a trip to formal charm.
You should project like a spotlight from the projector.
I had this whole notion on the first day of school to have like this big light and like light show to introduce kids to the class. And I don't know if you know Pink Floyd, but there's this really good song called Welcome to the Machine. And it's like this whole very light, and it would have been such a cool thing. And then I woke up. Now, I'm gonna start here because this should cover everything into what I mainly need to move forward from. Meaning, if you had trouble with Lewis structures, we're going to see them here. And then if you had trouble with resonance structures, we're going to see them here. And then this problem C especially introduces, how do I know if resonance structures are not exactly equal to each other, which is the best one, which is the most representative of the real molecule? So let's start with any one of A or B, your choice. Do you care? A is okay? A is okay. So I'll start since it's selenium oxide, and just so we can see. Oh, I guess so. Let me take the screen out of the way for a moment. And I'll write it a little higher up. So going through the bullet points of the method of how we write the Lewis structure. First, I count the valence electrons. I believe that is the number of valence electrons. Second, I lay out the atoms. So I'm going to just go this way. Some kind of symmetrical arrangement where selenium is in the center and the oxygens surround. Third, I attach all the atoms with a bond. That cost me 6 electrons already. Fourth, I go through and start satisfying the octets for the outer attached atoms first. And then I realize that at this point, I've run out because I have 24 total, and that's all I'm allowed. What did I do? Oh, thank you. That's 2 for 1. Now, given that this doesn't work because what's not yet satisfied, you have a selenium, I can push a pair in the middle, and we said yesterday that if we did this, it would satisfy all the rules, and it does. But what it doesn't satisfy is reality, because this suggests, as we said, one bond being different than the other 2, but it turns out that since all these oxygens are the same, that all these bonds are the same, and that they would fall into kind of a averaging of that last bond, meaning that 4th bond really kind of gets split 3 ways. So instead of 2 bonds here and 1 here and 1 there, it's all 1 1/3, and this is the result of what we call resonance. And so, because this specific assignment was meant to teach us about resonance, I had asked you to write all the structures. And in this case, it's not bad because all we have to do is move the double bond to each of the 3 possibly equivalent positions. So like here, I might draw the double bond on this oxygen, and therefore just move the electrons around accordingly. And here, I'll go to the other oxygen with the double bond. And really, these 3 pictures are not 3 different things. Their average represents the real thing. Which is why if I wanted to kind of explain what this little group of pictures is really saying, it's saying that I have a selenium atom that has 1, and this is going to look stupid, but I'm going to do it anyway, about 1 1/3 bonds on each side. Okay? I know that looks dumb. Deal with it. So each bond is equal, and that's what the measurements show, and has the equivalent bond strength of about 1 1/3. By the way, you might hear the term bond order. That's just counting the number of bonds between 2 atoms. So we would say this has a bond order of 1 1/3. Any questions about that so far? Or are we good? This is the time to ask if it doesn't click. Okay, well, let me make one last comment, and then I'm going to do the other example that illustrates the next principle. This type of resonance structures must be written automatically if there are equivalent ways to move that double bond or if it's a triple bond. So here I have to do it. It's required to really represent the true molecule. Like I told you, in the future, I'm not going to make you write them out every time. Here's how you're going to recognize it. If you just drew the first one and wrote res underneath, I will be satisfied with that from now on. So you can just indicate that you know it's a resonant structure because it needs to show the other possibilities. Okay? But if I ask you to write them, be able to. Okay. Now, I want to look at the very next one that was on the assignment, well, actually the third one, CNO negative. Can I erase this? Because that one presents a whole different situation. In other words, we are able to write valid resonance structures even when they're not equivalent. And there's reasons we would do that. But let me just show you how first. And then I'll show you how I know which one is the better one. So going through the same process, carbon has 4 valence electrons, the nitrogen has 5, the oxygen has 6, and then the negative charge adds an extra one for a total of, I believe, 16. Now, I'm going to leave the atoms in the order they are currently. And I'm just going to go through the same process I did a moment ago. So I'm going to start by bonding all the atoms together. Then I'm going to start satisfying the outer electrons, or outer atoms with electrons. But by the time I've done that, I've used up all 16. Now what? It seems like I ran out. How am I going to take care of nitrogen for a little old nitrogen? Yeah.
Put 2 double bonded in between C and N and N and O.
So push a pair here,
Yeah,
and then,
on the other side too.
and the other side too. That satisfies all the rules, doesn't it? Correct number of electrons, and every atom has 8. Everybody good so far? Was there another way we could have done it? You see, oh,
You put a triple bond on C or O and then a single bond on the other one.
so if we had done the triple bond, let's say here, and only a single bond here, let's just make sure that that's valid, because 2, 4, 6, 8, 10, 12, 14, 16, you still have the correct number of electrons, right? And every atom still sees 8. So this is another way that works. And then you also just mentioned the third way we could have done it. And the third way we could have done it is this. Because again, this follows all the rules we've learned so far. So the big question is there a reason or a way to know if one of these is better than the other? They're certainly not equivalent, because we have different atoms with more or less bonds. Whereas in my first example, it was the same atom each time around the middle. So this introduces us now to a method for being able to figure out which structure is best. And it is called formal charge. You might be wondering why it's called formal charge instead of just charge. When we think of ions, we think of charges because some atoms lose electrons and become positive, other atoms gain electrons and become negative. That's not what I'm going to show you here. It's still going to say pluses and minuses, but it's just a way to kind of get a sense of an atom's electronic environment. So what we're really gonna do here is we're gonna compare, I'll just say the electron environment of each atom in the molecule compared to by itself. Like, in other words, if we're not bonding to anything. So how do I do that? That's the real question. How do I kind of figure this out? For this purpose, we have to just understand how to count the electrons. If it's a lone pair of electrons, these only count on the atom where they are held. If it is the shared pairs of electrons, those are going to count let me put it this way. We're going to split them between the atoms that are sharing them. So this is a little different than we were learning how to count for the octet rule. Remember, for the octet rule, we let the ones in between count for both. But in this case, we're going to kind of split the electrons to calculate this formal charge. So for this to make sense, a couple examples should clarify it really quick. And then I'll explain to you, once you see how to get the formal charge, how to interpret it. Like, what is it telling me and what should I look for? So let me start with this first version of the molecule. Can you tell me, if this was just carbon by itself, how many valence electrons it would have, just sitting out alone? It would have 4. So when carbon is by itself, it has 4 valence electrons. But let's look inside the molecule where carbon is right now. And let's ask, according to this definition, how many electrons does the carbon have here? So how would I count them? Does this have any lone pairs? Does it have any electrons to itself? How many?
2.
1, 2, right? So these two are part of this carbon all to itself. How many electrons are in the triple bond?
6.
6. But we just said if they're shared, what are we going to do? We're going to split it. So of these 6, how many should I count for carbon? 3. So in the molecule, how many total valence electrons does carbon kind of have? 5. Now think about what that means. If carbon normally only has 4 electrons around it, but in this environment it has 5, how would we report that as a charge?
Minus
Plus
1.
minus 1.
Excellent, good.
I was first.
Excellent, good. So all I'm really doing is taking what it normally has and subtracting what it has in the molecule. You see that? You see how I'm getting that? Some of you did, obviously you responded. So I'm going to just take the normal number of valence electrons, so I can kind of make this into a formula if it helps you, but I think if you just see it, it makes more sense. I can take the valence electrons when the atom is by itself and subtract the total of the bonding electrons, sorry, start again, of the non-bonding electrons, the lone pairs, and half of the lone electrons. God, I keep flipping it in my head. Half of the bonding. It's so Friday. And that's why I don't really like the equation method, because you're like, yeah. If you just look at what I did here and do this every time, it's actually kind of simple once you remember how to do the counting. In fact, watch this. If you just start from the normal valence of carbon, you can do a countdown method and get there right away. So normally carbon has 4, right? Watch what I'm gonna do. 3, 2, 1, 0, -1. I'm just subtracting 1 electron at a time compared to where it normally is to get to the charge. Yeah,
So why don't the bonds count as the electrons in the bond?
because we're treating the bonds as purely covalent, and we're trying to give ownership in that sense. And if it's purely covalent, we split them equally, because we share equally if it's pure covalency. Like, I get 3, you get 3 for this purpose.
Yeah.
Can you read the equation one more time, please?
Yeah. So what it's saying is, and it's just what we did here, I take the atom I'm interested in, and first I ask, well, what would its normal number of valence electrons be? For carbon, it's 4. And then I subtract how many it has in the molecule to see kind of relative to what it's used to, what does it have now? Well, how do I count them? If they're the non-bonding electrons, I get all of them to myself. And that's why I counted these 2. And then here, we're splitting the ones we're sharing. And so that's why even though there's 6 between me and nitrogen, I'm only counting 3 of those. So the ultimate result then is that the carbon gets a -1 formal charge. Now let's try it for nitrogen, and let's see what method do you think will be easiest for you to figure it out. Yeah.
Basically, every time they share, you just split them, you
That's
split
it.
however many
Yep.
they share.
And then any ones it has to itself, it gets to itself.
Wait,
Like this carbon had 2 to itself, it's not sharing with anybody, so it got both.
okay, yeah. So for the oxygen, it would be like the 1 plus
You wanna do the oxygen? Talk me through it.
So it'd be the 1, I mean,
What
yeah,
does it normally have?
It has 6.
So again, just to help you visualize it,
It has 6 of those, and then you get 1 from the shared one because it's the line.
so it only gets 1 here,
Yeah,
and then how many of these?
6 of those.
So what's 1 and 6?
7. So it has 7?
So if oxygen normally has 6 on its own, but now it feels like there's 7,
Oh, and then you put the
what's its
-1.
charge?
-1.
For the same reason. And if you see that, we can do it again by the countdown method. Start at 6. 5, 4, 3, 2, 1, 0, -1. We get right there right
So
away.
then if there was 1 less, it would just be plus.
Yeah. And if you want to look at the equation, when you're doing oxygen, normally it has 6, right, by itself. But right now in this molecule, it has 6 electrons to itself, plus half of the 2 between these 2 atoms, which is 1. So you're doing 6 minus 7, and you get -1 again. Now there's 2 ways to figure out the nitrogen. We can do what we just did, but just like any other kind of charge, the net charge, which is here -1, is the sum of all the formal charges. So these have to add up to a total of -1. By that argument, what does the nitrogen have to be?
Plus 2.
Close? That would make it 0, right? It would have to be +1, but let's prove it by this method.
Wait,
Why-
what do you mean?
What do I mean by what?
Like, wait, can you speak English?
The sum of the formal charges
Yeah.
has to add up to whatever the net charge, overall charge. So if the whole molecule is -1, these little numbers, wherever they are, the
The
total
charge
has to add
up
to
to
-1. So by that, since we already have -2, to end up at -1, this would have to be positive. But to prove that the way I'm showing how to count, start from nitrogen, which has how many normally?
5.
5 when it's alone. Well, how many does it have in the molecule around it?
4.
1, 2, 3, 4. Right, half of the share. So 5 minus 4?
1.
+1, just like we said. Let's do the other versions before I tell you how to interpret this. Let's see if you can do this counting now. So can you tell me what you think the formal charge on this carbon would be?
5,
Close.
Wait,
6,
That's how many it has, but I'm asking what's its formal charge?
2,
Oh,
Oh, 1,
Minus
positive 1?
it's used to 4,
Yeah, -2.
minus
so here it has 1, 2, 3, 4, 5, 6, right? So isn't that -2?
is 2.
oh, it's formal minus,
It's the normal, what it normally has by itself,
okay, and then subtract.
and then subtract what it has in the molecule.
Next one's +1.
How did you get that?
It's 4 because 4 in
normally is 5.
1, 2, 3, 4. And when you take 5, which it's used to, and take away the 4, you're at +1. And what about the oxygen?
It has to be +1.
No,
Or it
it's
has to
just
be
the
0.
same.
1, 2,
It's
3,
regular.
4, 5, 6. Do you see why I'm counting the bonds only once?
Yeah.
Because each bond has 2 electrons and I only get half. So this is 0. Because normally oxygen has 6, and here oxygen has 6 to itself, and that's why I can come to 0. 6 minus 6. Let's look at the last one. What would the carbon's formal charge be here? Good, -3. What about the nitrogen? Try again? That's right. And the oxygen? +1, right?
Oh,
So what we're really looking at when we look at formal charge again is comparing the electron environment. So what the charges are telling me is, in this case, carbon has 1 more electron than if it were by itself. Nitrogen has 1 less. Oxygen has 1 more. Carbon has 2 more electrons than it's used to, et cetera, et cetera. That's what this is. But what does it tell me once I figure it out? By the way, did you notice they keep adding up to the total charge? That adds up to -1. That adds up to -1. So that's just showing me that we did it right. That doesn't prove anything other than we added it up right, yeah.
so do you always get the, like the charge of the whole thing?
You have to, otherwise you get it wrong.
Okay, but do you, like, on its own, so let's say we have like a problem or whatever, so will we get that charge or?
Oh, I see, yeah, if
Sometimes
there's
we're gonna
no
have to-
charge stated, it's just neutral, so the charge
Okay,
is 0.
So there's no charge stated, it's neutral. So then they would have to add to
Yeah, exactly.
it, okay.
Now, before I even explain how to apply this, look at those possibilities and tell me which one feels like the best and which one feels like the worst. Can you give me some insight into this? I just want to see what you think before we talk about it.
Wait, what do you mean?
Of these 3 possibilities, they're all different, right? Which one do you like? You like the middle one. We have 1 vote for the middle.
I'm in on the middle.
I like that one.
What do you like?
I like the last.
The first one?
Yeah.
This one?
Yes.
2 votes?
The last one?
The last one?
Yeah.
Middle.
The middle again.
The first one.
The first one. Joseph, you were the last to say the first, so I'm going to lean on you. What do you like about the first one?
The fact that they all have 1. I like that.
That's a good thought. What do you like?
They're all just like evenly distributed.
Evenly distributed. Let me ask you a question, because I think I can really clarify this concept of what this is about and what's, the stability. And I can prove it with a very simple example. Ready?
What is that?
Is that making you nervous? Okay. Watch this. You didn't get nervous. Why did you? So what? What difference does it make? So,
Did you like, let her know?
one of these days it's going to slip. What I'm trying to tell you is this. If you have all the charges equally spread out in a molecule, like if everything had a 0 formal charge, right, everything would be evened out, it would be like a rubber band that's not stretched. But when you want to separate charges, remember they attract each other, right? So when you separate charges, what are you doing to a molecule? You're putting in more energy, and that makes it less stable. That's the first thing. So the first thing I want to tell you about this then is, in terms of what makes a good formal charge setup, the first principle is you want to minimize the formal charges. And that means 2 things. 1, you want the fewest, meaning you want as few atoms as possible to have to carry a formal charge. And 2, you want the least. Well, let me say that different because it sounds the same. You want the smallest. Meaning if you're going to have formal charges, you want the charges to be closest to 0. So seeing a -3 charge right away to me is a big red flag. That's a lot of formal charge. And that means there's a lot of kind of energy to separate that charge in the molecule. The next thing you want to consider is who's carrying what charge. Shouldn't the most electronegative atom carry the negative charge? In other words, does it make sense that carbon is yanking all this electron density away from these very electronegative atoms? Right? That doesn't make sense, because it's like saying the weakest person is pulling and winning the tug of war. But these are much stronger. So this picture does not look good to me on both counts. It has very high charges. And there's another thing. What's another thing that's absolutely offensive in this one? Look at it carefully. No, not the triple bond. Look carefully about charge. I'm looking at charge. It's absolutely offensive. It should make you almost yak. Hmm?
I don't have that strong of a feeling towards many things.
Yeah.
There's two positive charges.
Oh my gosh, that's repulsive, literally. Get it? Get it?
Oh, you're making a video?
Oh.
Okay, good, thank you. That's awesome.
So, absolutely horrific. You should have a strong reaction. If two like charge, even in this fake charge system, are next to each other, this is horrible,
Why?
because they repel. You're forcing a much higher energy into the system, because now you're making things that are trying to push apart stay together.
So is it bad if you write it like that?
That's what he's saying.
That's what I'm trying to say.
So we should never ever write it like that?
What I'm saying is this. Right now we have 3 resonance structures, right?
Yeah.
One of them is better than the rest. What I'm saying is these are the principles that kind of tell us who's the best. You want to make the least amount of charge, and you want the charges to make sense. So if you look here again, carbon is much less electronegative than nitrogen or oxygen. So again, this is kind of offensive that carbon's winning the tug of war. Both of these pictures are pretty bad. This one is probably the least bad from the ones we have, because even though each atom carries a formal charge, at least the oxygen, which is the most electronegative, has a negative one.
Okay.
And the carbon, which even this is kind of next to nitrogen, because nitrogen pulls harder. No, but at least this seems to be the least offensive of the 3. So I would suggest that if this molecule exists, this picture is probably the best one to describe the bond.
Yeah, I'm a little confused. When you say like that one should be pulling more, is it because,
Remember the trend in electronegativity?
yeah, like whichever one goes to the right?
To the right.
Yeah.
Pulls harder.
I do, yeah, okay.
Now let me show you how this rules in and rules out some obvious things. Okay? Take a look at like CF4. If we did the Lewis structure for CF4, we get 4 for carbon plus 4 7s, that's 32. And if we drew it the way we were kind of going with symmetry the other day, it would very quickly come to this picture. Now, if we do a quick formal charge check on this, what would the formal charge of carbon be? Hopefully you're going to see this quicker and quicker as you go.
Or
0.
0.
Careful, you're answering the wrong question. You're telling me how many electrons it is. I'm asking for the already subtracted value. It normally has 4, and it gets to count 4 in the molecule. The difference,
The other one is 0. Or no,
this one is
what's this?
6,
0.
Isn't it normally 7?
7,
1, 2, 3, 4, 5, 6, 7.
Yeah, it's like 7.
And if it's like that, you don't have to keep counting. Aren't these all in the same boat? Isn't it 0 everywhere? You can't beat that. That's ideal. Like, that's the best situation. You can't get any better than that. But let me show you now how symmetry is consistent with what we're saying. Because could we have drawn the structure this way and made it work with all our other rules? Let's find out.
Wait, no, you can't.
Let me just count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, 6, 28, 30, 32. Doesn't this follow all the octets and everything?
Yeah, but it won't count the same because, oh wait, maybe it will.
No, it won't.
Wait, no, it won't.
Watch how bad this is. This should make you not only vomit, but want to run headfirst into a wall and just knock yourself out. This is how bad this should look. Avert thine eyes! You see this fluorine is still in the same situation as this one. So I can see that's a 0, and that's a 0. Do you see this fluorine is in a different bonding arrangement? What would its formal charge be?
-2.
Huh?
-1.
I heard 1, 2, 3, 4, 5, 6. 7 minus 6. And this is also +1. What would the carbon be?
Minus something.
I have to describe this quickly. I'm about to have a heart attack.
0, what? Isn't that what kind of side effect?
Fluorine is really far away.
0.
What's the most electronegative atom?
Fluorine.
Fluorine. Look at what's happening. Carbon is taking electron density away from fluorine?
It's all
Are
right.
you okay?
There's positive fluorine! Help!
Francis is dying.
Yeah. I was trying to be dramatic. Didn't work.
You're already.
Can you see what I'm getting at?
Yeah.
Now this is why also fluorine never forms anything but one bond. If fluorine, the most electronegative atom, did anything but this kind of structure, it would always become a positive formal charge. It's never going to happen for fluorine. That's why you're never going to see something like this. Because that forces fluorine into a positive formal charge. It's never going to happen. So this formal charge technique lets us figure out if there's similar structures, which one is better and which one is less better. Yes? Oh, let me do one more. And then you do have an assignment on this over the weekend
Hey.
that will be due on Monday. So, listen, I think ladies and gentlemen, I appeal to you. I have done everything I can to reduce the homework for these children.
Not enough.
Why you? Is it wrong? Is it wrong to want learning? Is it wrong to need practice to perfect one's art? Is it wrong? I ask you,
Just the way the most popular video.
what must a chemistry teacher do?
And scene.
Nice.
Thank you.
What an actor. You should be an actor.
Improv.
Honestly. Alright, this is so much work. Don't be an actor.
How do you know I'm not an actor pretending to be a chemistry teacher?
Like how you do it?
How'd you get those credentials?
How you
I
do
studied
it?
the part.
It's called forgery. Okay. go
This
ahead.
is one version of carbon dioxide, but another resonance form could have been this.
Resonance.
Again, when I say resonance, it just means I've moved electrons.
Yeah.
Let's prove which one is better.
It's the top one. I already called it. That one has 0, 0, 0.
Wow, you see?
So cute.
Because watch it, ready? Watch this. Does it have 6? Normally? Is this there? 1, 2, 3, 4, 5, 6. The difference is 0. This is the same as that one, that's 0. It has to add up to the overall, so that's 0.
Wow.
Huh? No, 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 no. Once you see it, it goes like that.
Check out that.
Now let's do this one. You do this one, I missed the parachute.
No.
Go, 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 go. What? So take your time.
There's 7.
Quiet you.
How?
How many count? How many count here?
That's for what?
The total electrons are on this oxygen.
No. Oh, 7.
It's 7 based on what we're counting now. You were right about 8 if we were doing like the octet rule. But as far as the formal charge, it's 1, because you only get half of what you share. 2, 3, 4, 5, 6, 7. What does actually oxygen normally have? 6 minus 7. Carbon only gets 1. 4. What does it normally have?
4. Sorry.
How many does this oxygen get?
Oh.
What does it normally have? Six minus 5.
Yes,
Which is better? Which is better?
It's
The homework is this. Go to commercial.
No, commercial break.
Commercial break.
Fiona.
Fiona, do the commercial.
What do you mean me? You the one who